How can a machine rolling on ordinary highway tires move cargo weighing hundreds of tons without collapsing the road beneath it or tearing itself apart? Right now, across deserts, frozen highways, industrial corridors, and remote construction zones, trucks are doing exactly that, routinely hauling loads that should be impossible for anything on wheels. The answer begins not with a truck manufacturer, but with a Cold War arms race. In the late 1950s, military planners faced a dilemma that would quietly reshape the world's highways. Railroads, once the backbone of heavy logistics, could be destroyed or bypassed in a modern conflict. The Soviet Union responded by commissioning the Ma-537, a machine designed not for speed or comfort, but for the relentless, controlled movement of extreme weight over any terrain. Debuting in 1959, the Ma-537 was a 30-ton, 6x6 tractor capable of towing artillery, missile launchers, and even bridge sections, weighing up to 100 tons. Its high-clearance chassis, hydraulic winches, and modular frame rails were built to conquer mud, snow, and broken roads where trains could not go. The Ma-537 did more than move military hardware. It established a blueprint for every heavy-haul truck that followed. Red Army engineers prioritized low-speed torque, multi-axle traction, and the ability to spread weight across soft or damaged ground. These features made the Ma-537 a legend in defense logistics, but they also laid the groundwork for civilian machines decades later. When the Cold War ended, surplus Ma-537 vehicles and their technology found new life in oil fields, logging camps, and construction sites from Siberia to Central Asia. Demilitarized units, stripped of classified equipment, were sold or adapted for commercial use. The same hydraulic systems and modular chassis proved just as effective at hauling turbines and mining rigs as they had with tanks and missile launchers. The problem these machines solved was never just about raw power. It was about delivering the heaviest loads to places no railway reached, under conditions no ordinary truck could survive. The Ma-537's legacy is visible today in every modern heavy-haul convoy. The insistence on redundancy, the focus on weight distribution, and the careful balance of traction and control. What began as a military necessity became the silent workhorse of global industry, carrying the seeds of a new engineering philosophy from battlefield to business. A heavy-haul truck faces a challenge that looks impossible at first glance. How do you set hundreds of tons in motion, inch by inch, without tearing the vehicle apart? The answer lies in torque multiplication, not raw horsepower. Unlike a highway tractor built for speed, a machine like the Oshkosh M911 is designed to crawl forward with unstoppable force, even when a single wheel must bear the weight of a tank or a turbine. The engine is only the beginning. The real work happens in the deep reduction transmission, an intricate stack of gears, shafts, and planetary sets that transform the engine's rotation into a slow, relentless pull. The Oshkosh M911, for example, uses a multi-stage gearbox with an overall reduction ratio as high as 45:1. That means for every 45 turns of the engine, the wheels rotate just once. This gearing allows the truck to move at walking speed, while delivering axle torque that would shred an ordinary driveline. The transfer case located behind the main transmission splits power evenly between axles and offers selectable low-range ratios for the heaviest hauls. Each shift drops speed further but multiplies force, making it possible to start a 70-ton tank from a dead stop on a steep grade. Gear teeth in these systems are cut from hardened steel, sometimes more than an inch thick, and the entire assembly is built to withstand torque surges that spike far above the engine's rated output. Electronic controls now monitor gear selection and throttle input, keeping the drivetrain in its optimal torque band and reducing wear. The result is a vehicle that can move a load weighing as much as a small ship, because every link in the driveline is engineered to handle forces that would destroy lesser machines. Before a single pound reaches the road, the mechanical path from engine to axle has already tamed the impossible. A truck hauling hundreds of tons across an ordinary highway looks like a recipe for disaster. The weight alone seems enough to crush asphalt, buckle bridges, and leave a trail of destruction with every mile. Yet these convoys move without tearing up the roads beneath them. The secret lies in how weight is distributed down to the last kilogram through the suspension and tire systems. Every axle added to a heavy haul truck is not just for show. It is a civil engineering solution designed to spread the load so that pavement stress stays within safe limits. Consider the Pacific P Hull, a platform built in the 1970s for Canadian logging roads and later adapted for bridge and turbine moves. Its designers faced a simple problem. How do you carry a 120-ton log or a bridge girder over a rural highway rated for far less? The answer was to multiply axles and optimize the suspension so that each tire presses against the road with no more than 0.27 megapascals, comparable to the pressure of a fully loaded city bus tire. That figure is not random. It is the result of careful contact patch calculations, ensuring that even as the total load climbs past 100 tons, the force per square centimeter remains manageable for the underlying asphalt. Hydraulic suspensions and load equalizing systems play a central role. Unlike leaf springs, which can leave some axles overloaded on uneven ground, hydraulic modules constantly adjust to keep weight balanced. The Pacific P12 system allowed for fine-tuning on the fly, even as the truck crawled over frost heaves and potholes. This approach protects not only the truck, but also the public infrastructure it travels on. It is why modern heavy-haul trailers use modular axle lines that can be added or removed as needed, scaling the contact area to fit the route and the cargo. What looks like overkill with dozens of tires, complex suspension arms, and sprawling trailers is really a precision tool engineered to make the impossible possible without leaving scars on the road. A convoy moving a 100-ton transformer or a 300-ton reactor vessel does not rely on a single truck or even a single trailer. The real muscle comes from modular systems, self-propelled modular transporters, SPMTs, engineered to scale up axle by axle and module by module until the math matches the load. The formula is simple but powerful. Total capacity equals the number of modules times the number of axles per module times the rated load per axle. For a Nicholas SPMT, each module might have 4 axles, each rated at 12 tons. String together 8 modules and the system can legally support 384 tons, with a built-in safety margin for dynamic forces and uneven ground. But turning that engineering possibility into a real-world move demands more than steel and hydraulics. Every route is a puzzle, and every piece of paperwork is its own engineering challenge. The permitting process stretches out over months, sometimes up to a year for the most complex moves. It starts with a feasibility study. Engineers calculate axle loads, check bridge ratings, and model pavement stress. Even a single weak bridge can add weeks to the timeline, requiring custom shoring or temporary reinforcement. Once the route is mapped, a cascade of agencies gets involved. Departments of transportation review every calculation. Utility companies plan for power lines to be lifted, pipelines to be shielded, or traffic lights to be removed. Law enforcement schedules escorts and traffic control. Public notices are published and neighbors are warned. Across the United States, Europe, and Australia, it is common for the full approval cycle, route survey, agency sign-off, public review, and pre-move preparation to take 6 to 12 months. Delays are measured in weeks, not days, and a single missing permit can halt a project worth millions. What looks like a slow-moving parade of steel and tires is actually the end product of thousands of calculations and signatures. Every axle, every escort, every detour is the result of engineers and regulators working together to make the impossible possible. Only when the paperwork is as precise as the machinery can the convoy roll out inch by inch toward its destination. A heavy-haul convoy is more than a collection of steel and rubber. It is a living system, animated by human expertise that turns raw machinery into a precision tool. The Kenworth C510, hauling ore across the Pilbara, is a prime example. Behind the wheel, a driver manages not just the throttle, but a shifting landscape of traction, axle loads, and road conditions, making real-time decisions that keep hundreds of tons in motion. Alongside, an engineer monitors telemetry, fuel burn, tire pressure, and suspension data, ready to intervene if a parameter drifts out of range. Regulators pore over route plans and bridge calculations, clearing each kilometer only after every load and stress value checks out. Escort crews coordinate traffic, manage rolling roadblocks, and scout for unexpected hazards ahead. On a 420-kilometer haul carrying 180 tons at an average of 30 liters per 100 kilometers, each roll is essential. Without this human network, even the most advanced truck would stall before reaching its destination. A week-long convoy unfolds as a test of everything heavy-haul engineering has promised. Each morning, the team checks tire pressures and suspension settings, recalibrating for the day's stretch of highway. The convoy inches forward, every axle and module working in concert to keep pavement stress within limits. At bridges, operations slow to a crawl as engineers confirm load readings and escort crews guide traffic. Overnight stops become rolling workshops. Mechanics inspect hydraulic lines, drivers review route changes, and regulators sign off on the next segment. The plan's logic becomes visible in motion. Hundreds of tons glide over asphalt, bridges flex but hold, and the road beneath remains intact. What seems impossible, moving a mobile industrial system across public infrastructure, proves achievable only through this relentless, coordinated choreography. What looks impossible, hundreds of tons rolling over ordinary roads, rests on invisible networks of engineering, planning, and precision. As global industry demands ever larger infrastructure in ever more remote places, these machines quietly expand the boundaries of what roads and the people behind them can achieve. They redefine the limits, 1 mile at a time.